Okay, since we have most people here, the remaining should filter in soon. We'll get started. Priya will tell us more about the basics of black hole accretion.
Okay. Okay, Chris, could you just get some water for me?
Sure, yeah.
Okay, so now for a complete change of tone from Roman's excellent talk. So what I wanted to do was to continue a little bit from what I covered yesterday, just wrap up a few ideas in thin accretion disks that we outlined yesterday. And then I'll just sketch out super Eddington accretion, just in terms of the geometry, what it requires. And then we'll move on to models of black hole feedback. And I will focus on sort of outflows and winds because there's a lot of, as you know, a lot of the modeling that I'll be talking about in the final lecture, the sort of the basic work that I'm doing now is in service of explaining and accounting for the kinds of scaling relations that I'll be adopting, right? So they all come from these kinds of simple frameworks. And the goal, of course, is to tie and match as many observations as possible. So the observational evidence for outflows and winds is very strong at the moment. So I'll show you a little bit of the data and how that has informed the kind of feedback models that we have developed. And so, you might have noticed that so far, you've heard these excellent lectures from Eve about the details of the ISM. And, and I've been kind of floating in the sense I've been just telling you about this sort of isolated black hole and right around the vicinity of what's going on in the black hole. So ultimately, to make sort of any kind of feedback model, right, you really do have to couple the black hole and the inner regions with the rest of the galaxy. And so the kind of feedback models that I'm going to be talking about are just a couple of simple heuristic ways that are now implemented both in simulations as well as in sort of semi-analytic models for coupling the small scale to the large scale. And as you know, if you look at as a function of galaxy mass, you look at the most massive black holes in the most massive galaxies, they appear to play a very important role in modulating the star formation, quenching, and so on. So we're going to ultimately, I won't be deriving the kind of detailed model coupling the inner region to the outskirts, but you now have a really good flavor for the ISM and the physical properties in the ISM. So at some level, what I'm going to do is kind of pick processes that Eve has talked about that are going to be relevant for coupling and try and see if it matches the observations. Obviously, I'm showing you, I'm not playing because I'm going to show you models that kind of work, right? Ultimately. So I've added a few more, actually two more reviews here. One is actually a paper by Gaspari and Sadowski, which offers, I'll close with that. That's a slightly different view because it's a view in which they have adopted these scaling relations in a very sophisticated GR radiation MHD code. And by way of, it's the last slide because it's by way of validating the sort of the simple picture that I have to show you that even the most sophisticated simulations at the moment are sort of incongruous with this understanding. So let's just continue back for just, the basic stuff once again to remember, I've been telling you that our goal is always to try and explain all observed phenomena as much as we can with the simple set of heuristics. So we saw that you could model an accretion disk basically as rings or annuli, and these annuli, and we talked about the shearing between the annuli, which is the source for viscosity. And so now these annuli each of the annuli can be treated as black bodies. And so from the dissipation rate that we calculated, but remember our star is the inner scale, and ideally we'd want to be able to capture the physics at the ISCO, but we know that it's the inner edge of the accretion disk, right? And so we can then compute what a template spectrum, so keep track of the colors here, I remember the colors for just a minute, and then one can actually calculate in the approximation that the dissipation rate can be modeled as black body flux, sigma t to the 4. It's a function of r that allows us to compute the temperature as a function of r. And so you get this profile for the temperature. And so then the output spectrum that you want to create for any model template basically is the sum over these black bodies. This is for the disk itself. So what is not included here is the further interaction of extra structure, for example, the corona above the disk and so on. So that stuff, and then absorption by the gas that is external to the disk, but in the vicinity of the black hole, further in, further out, so on. So we'll see about. So we're going to be, to get the final spectrum, you're going to be adding all these processes. But the key piece that we've focused on so far is sort of the disk. And just have a few observed spectra on the top to kind of show you that this general idea of a sum over black bodies is not crazy for the disk itself, although you see other features that show up, and we'll see what those features are in a minute. And just to kind of remind you that, the emission actually spans a range of photon energies, as we saw yesterday, and therefore there's a lot of processing that these photons can do as they leave the inner portions of the galactic nucleus. And as people have asked, in many cases, there's also a large amount of energy that's transported and deposited in relativistic jets. And so I'll talk very briefly because questions came up yesterday, because as you've noticed, I've sort of steered clear of magnetic fields, really, because you can't really do closed analytic solutions with when you have magnetized disks. You can do some approximations, but it's too complex and it's not useful to just flash those equations. Okay, so this was a picture, a rough picture of the distribution of material right around it. This is relevant for understanding the emergent spectra, because this is the kind of scale that we've been dealing with. So this is the sum over black bodies that I've been talking about. And so then you have the radiation, as we saw, ranging from optical, UV, X-ray to gamma rays, and then you have all this crud around it. So you have the broad-lined region, you have these blobs of gas. So there'll be a lot of processing. So you can see that the emergent spectrum is going to have a signature of radiation filtering through the structure, and you can also very obviously see that depending on your viewing angle, you are going to see domination of a signature of certain kinds of processes, right? So you have a jet that is pushed out, and then you have this narrow-lined region. Once again, you have blobs, right? And we believe that outside the sort of the inner accretion disk, we also believe that there is sort of this donut-like obscuring torus structure. And so this picture, by and large, does not hold, obviously, for all AGN, even regardless of the viewing angle giving, there's a zoo of AGN. There's broadline quasars, there's narrowline quasars, there's Seifert1, Seifert2, and that whole zoo was classified on the basis of the viewing angle, right? So it turns out that the picture is slightly more complicated, but this is a good kind of heuristic picture to have, just to understand the additional components that you're going to get from the accretion disk spectrum when we look at active galactic nuclei. So, and I think this is also, I stole this slide from Mike Iraculis, who gave a really nice talk here a few months ago, in response to a question that someone asked me, right, about the scales. And I thought it would be good to just go through some of the numbers. So if you started with a central black hole that's 10 to the 8 solar masses, and say it's accreting at 0.1 Eddington, so it's not maxed out at Eddington, then the reason that's important is, obviously a lot of these quantities are going to scale with the luminosity. But if you look at what I want you to focus on is, the broad-lined region, where I just showed you in this picture. You saw the broad-lined region that's right around outside the inner accretion disk, but right around. So that's about 1,000 Schwarzschild radius, which for this black hole mass corresponds to 1/100th of a parsec to 1,000th of a parsec. And in terms of sort of observationally, that part is actually unresolved, which is sort of a plus and a minus for theorists, because if it's a plus because then we can build models, and they can't be completely kicked out. But they have to fit in with the rest of the scales, right? We have freedom, therefore, for modeling the outflows and so on. And then you have the inner edge of the torus. You saw this sort of torus, sort of donut structure. We're talking about 0.1 parsecs. And then the narrow line region, the crud that we saw far out, that's narrow line blobs, right, that are actually quite far out. And they're almost at 10 parsecs for this example. And then the larger scale ionized outflows and stuff that you actually observe, that are actually seen. And as I was telling you now, a lot of the feedback models, when I say they have to be consistent with data, we are actually talking about sort of these kinds of scales, where we see the winds and we see ultra-fast winds and outflows. And so that's what we're trying to match. So as you can see, we need to scale and build a model already that starts from about 10 to the minus 3 parsecs, and we're sort of 6 orders of magnitude in terms of where the real observable constraints are coming from. So this is just a caveat to tell you that there's still a little bit of freedom in terms of picking the models, but they have to kind of match. So we have these places where they have to match with the observation. So so again, once again, this is just the typical sort of AGN spectrum. And what I wanted to show you is the sort of variation in the shape and the amplitude, depending on sort of this zoo of classifications, whether it's Seaford 1, Seaford 2, as I said, which is a viewing angle thing, and whether you have radio quiet or radio loud sources. So I think part of the one sort of generic feature that you saw from the sum over black bodies is that you have this ultraviolet far UV big blue bump. So that's sort of a feature that you see by and large, regardless of viewing angle, you see that. Okay? On top of that, you'll have modulations. So another sort of interesting feature of the spectra, which had not really been included in modeling the black hole population, which is what I'm going to finally talk to you guys about. How do we go from this sort of understanding of the physics around sort of an individual galactic nucleus to modeling an entire population of black holes? Because ultimately, we are seeing quasars. We are seeing the quasar luminosity function is a function of redshift. Those are the observed quantities. And that's what we want to predict and match our models with. So it turns out that this was this is short timescale variability. And so when you have really good data and you see the light curve, you see a lot of variability. And this variability, you understand, actually comes from the fact that the time scale is about 10 to the 5 years or so, and that actually tells you the sort of the size scale on which in the nucleus from which this variability actually arises. So there's a physical process. So even if we don't model and know the exact details of what is switching things on and off and flickering, what we now know is flickering, short timescale variability, is an ingredient that would be useful to include when we do the demographics of an entire population, because that seems like a fairly ubiquitous property. So as you'll notice on my final lecture, that all these elements are going to be included in that model. And that's why I've been focusing on these particular elements. So flickering is going to be, so short timescale variability is going to be a feature, and we will see why and how adding that feature is helping us match the luminosity function of quasars. Actually, it helps us match better. And again, there were a couple of questions at coffee yesterday, so I added some of these slides, where the question was, on top of this simple inner region, what are the other regions of the accretion disk that manifest in the emergent spectrum? So you have the corona, which is above the disk. It's hot gas. Basically 10 to the 6, 10 to the 7 Kelvin. And these X-rays, and I think it was Pascal who was asking me, and it's these X-rays, actually, they irradiate the disk, and they alter the spectrum. And we believe that they can also alter the geometry of the accretion disk itself and the physical properties of the disk. So, and this torus, this torus that I just showed you in the cartoon, actually we think that there's a lot of dust in the molecular torus. It has molecular gas. It absorbs the optical UV part of the emergent spectrum geometrically. Because it's a torus, the radiation along the disk plane is absorbed in the optical UV part of it, and the dust gets heated, and then you get re-radiation in the infrared, so you see some infrared signatures. So it's because you see the infrared signatures, we've inferred that there has to be some kind of dust repository very close to the accreting black hole. And then you see broad and narrow absorption lines, and what's interesting is you see very high velocity outflows. And especially in the last few years, there's been a lot of data from Chandra that is showing us evidence for very high velocity outflows. And you know, the regions, the exact regions from which all the lines arise are reasonably well understood for the most luminous cases. We don't actually know for very low luminosity AGN. Because you don't actually have this kind of resolution spectra for them. We don't actually have as good an understanding of the spatial correlation of where we think the energy that we are seeing, particular portions of the spectrum actually arise from. And although I'm not really going to be talking much about radio galaxies and jets, it would be remiss of me to not actually show what the typical radio galaxy looks like. So essentially, you have a jet, you have these lobes where basically looks like radiation, matter entrailed, has been pushed out, very, very high velocities, ultra-relativistic velocities often. But then there's a hot spot where the jet kind of hits the ISM material, shocks, glows, and you see the hot spot. So this is the hot spot at the edge of. So essentially, this is what we think is happening in a cartoon. So, and you have some material that probably flows back, and so on. So, okay, so let's now come back to talking about thin disks and, you know, sort of the perennial question of, you know, what are the physical conditions? Which galactic nuclei are well modeled by thin disks? Because it's pretty clear it was an ideal sort of solution. But as I mentioned yesterday, the thin disk conditions actually hold for a very large number of cases, particularly for bright quasars at high redshift. So it's a pretty good description of all the observational signatures and data that we have for high Z quasars. For nearby sources, we actually find that the thin disk approximation is not so great. That's because the geometry of the disk itself in the inner regions is different. So it's thick, which means that it's thick, and it can be more spherically symmetric, if you will. And it's sort of a fat disk, sort of fattened disk. And there the Keplerian approximation breaks down. And this kind of configuration does not actually cool very rapidly because you can actually trap radiation in that blob. Okay? And so there's been a lot of progress in calculating. So thick disk solutions, I mean, there is an analytic way to in which they're tractable, but it's very complicated. The easiest has been looking at simulations in particular. And calculating flow timescales and to see how different they are. So I urge you to take a look at the GR MHD simulations. There are some really nice simulations by Jim Stone and collaborators, Charles Gammy and collaborators that show you sort of a different geometry from what we've looked at, which is the simple one that is analytically tractable. So the one interesting possibility, right, is our cases for which there is a class of analytic solutions, and I will just be showing you what the solution is. We're not going to derive that. Okay? And so this is the case where you have an advection-dominated accretion flow. Basically, matter flows inwards without radiating, so you could have a very high mass accretion rate and very low luminosity output. Okay? So that's basic basically what's happening in these cases. And we think that this is the kind of geometry that explains what's happening in a lot of nearby galactic nuclei. So there's a set of analytic solutions that Ramesh Narayan and Yi came up with for these. And numerical solutions have kind of shown that that sort of analytic model roughly works, except that one of the key features that we are not able to capture in these simple analytic models is what fraction of the gas that actually goes in gets pushed out in outflow. So ultimately, because remember that we really need to feed the gas down to a lot smaller scales than we actually have adequate descriptions for, right? So we know that the gas will probably go in, but not all of it might go in, and a fraction of it is going to be pushed out in outflows, so you don't actually feed the black hole as efficiently under certain circumstances. But the key thing is what fraction makes it in and what fraction gets pushed out, right? So let's come. I realized yesterday that I talked about the viscosity parameterization, but I actually didn't mention alpha. So let me just put the alpha, because they're called alpha disks for a reason. I told you everything that it was, but I just didn't tell you it's called alpha. So this viscosity nu, which we saw yesterday for, it's a typical length scale, and this is in that shearing model for describing angular momentum, the torque that is generated, the shearing torque, and the angular momentum transport that is facilitated by this viscosity. So this viscosity can be written as alpha times Cs, the sound speed, times the disk scale length h. And so one can argue from the fact that typically for the thin disk that we've looked at, that lambda, which is what we modeled the viscosity as, is less than the disk scale length, and that the random motions, the velocity of random motions u, has to be less than the sound speed. So with that condition, with that proviso, that tells you that alpha actually has to be less than 1. Okay? But there's no reason to believe that alpha is actually constant, and the models, these ADAF models where you look at advection-dominated flows, this actually alpha is a function of m dot, as you can imagine. And again, in response to a question about what are the other kind of effective ways in which viscosity, aside from this kind of hand-wavy alpha prescription, obviously one other important mechanism for generating kinematic viscosity is magnetic fields. And partly, not just magnetic fields, but the field configurations and the instabilities that those field configurations impart to the accretion disk. So for example, if you had a magnetic field threading an accretion disk, then the magnetic tension tries to basically straighten the line, and you have an imbalance between gravity. So you have a rotating disk, imbalance with gravity and rotation that will tend to stretch the line. And the vertical feed line will get perturbed towards the outskirts, and which is a portion of the disk, and where the centrifugal force is exceeds that of gravity. So you get kinkier as you get pulled out. And then the line will basically, the field will reconnect with the fast-moving inner matter, with the slower outer matter. And so you have sort of a mechanism in which the changing geometry of the field lines can effectively transport angular momentum out. And so this sets up this instability that is called the MRI instability that Balbus and Hawley came up with, and it's now been tested in these high-resolution simulations to show that this actually kind of operates, and it's and the limits of when it stops operating is if the B field is too strong, then this instability can actually be suppressed. So, or it can be amplified or suppressed. And the simple way to think about what's going on is in the presence of a B field, you have the B square over 8 pi that you add to the total pressure on the inside, and you have the gas, just the gas pressure out. So what you end up happening is having these flux tubes that will actually rise because of the difference in pressure, And so you sort of have, you generate a new sort of vertical field that then closes back in. So you sort of generate this instability. And numerical simulations have shown that this can be sustained and that it works quite effectively. So although we don't have a, as you can see from just the fact that I'm saying, well, you need to see this numerically, that is the attraction of the alpha prescription, right? That you can really understand very simply, even though it's not a fully microscopic description. And so again, the reason why the MRI is interesting is because we already know that we see these very, very collimated jets, and that having magnetic fields, like basically having magnetic fields be an actor in this story that I've been talking about is really important, because that can also explain why the jets are so collimated. You need magnetic fields to collimate the jets, to launch them and actually collimate them. So the whole idea of how jets are launched, how they propagate, is not a fully solved problem at the moment. So there's been a lot of progress. And much of the progress, I think, has been, as I said, there are a couple of groups, Jim Stone's group and Charles Gammey's groups, and you can go take a look at some of the videos and the movies they've created with their simulation results. Okay, so let's go back to now trying to motivate the kind of feedback model that we're going to need, right? So the first question, before I do that, let's look at what are the circumstances under which you can actually bypass the Eddington limit. So remember, the Eddington limit was derived with a strict set of assumptions about the geometry. And what we can see, if somehow, and we use the fact of sort of balance to get the Eddington criterion, but if somehow the radiation that you are getting from the accreting black hole can escape without really interacting with the matter, right, then you can circumvent the Eddington limit, right? And radiative transfer calculations actually show that. So how would it work in terms of just physically understanding what's going on? So notice that in your normal Eddington accretion, so you have the mass flow, and I've sort of suggestively drawn this sort of blue blob and this green region here, marked it out because that's sort of where you're going to see outflows, right? So you have the mass supply rate, the accretion rate, m dot of r, and we know that in order to stay at the Eddington limit, m dot of r just has to be proportional to r, and you remain at the Eddington limit. However, if you look at the case when the average photons can basically give up their momentum to an outflow, and an outflow that will actually escape, so you have these, most of the photons will escape along the axis there, then what you can do is you can actually get a luminosity in which the proportionality now is with the log of the accretion rate. Okay? And of course, in this case, you have some beamed radiation that's coming out. So the kinds of objects that you could infer are likely undergoing super Eddington accretion. Some of the features that you should see are sort of heavily beamed. So at the moment, observationally, we have only one object where we see all the features where this roughly matches, and that's SS433, a source. I urge you to look that source up. Okay, so that's all I really want to talk about super Eddington accretion, except what I want you to take home from there is that it's a mode in which the luminosity is going to be proportional to log of the accretion rate. And for the standard Eddington accretion, remember the output luminosity is directly proportional to the accretion rate. So in terms of scaling relations, right, that's what we're going to get out of this understanding. So we will be looking tomorrow when we look at propagating a population of black holes, that there will be two kind of accretion models that we'll be looking at. One in which the output luminosity, so these are the two cases, and this is what we've sort of extracted from our work so far in terms of the scaling relations to model a black hole population. So once again, just to remind you, so all of this, right, so now I've explained a lot of what is going on at the level of not just the galactic nucleus, but the inner region of the galactic nucleus. And the goal is to now embed this in the larger picture of galaxy formation. And this is just a little cartoon that shows you that we know there's hierarchical merging in the universe. And so we have to do something in terms of our modeling to capture the merger process and how that impacts accretion and the output from accretion. And what the merger does to the rearrangement of mass in the inner region. So the gas reservoir, do you have outflows? Do you have a lot of winds that push out a lot of gas? Does the gas fall back eventually? This is on larger scale. But we kind of have to now put our little picture of the tiny black hole in the center back into this larger scheme. And once again, I just want to reiterate, you might say, you just saw Roman's talk, and you're seeing what we can do. We do some very impressive things with simulations, but we still can't quite go all the way from a full cosmological box. And that's why, luckily, there's room still in the game for people like me who are thinking about sort of the, looking at the small-scale physics, simplifying it, and see what can be adopted to actually run simulations which might capture all the relevant physics. Because the resolution, the trade-off with resolution and volume might actually not allow you to do the problem ab initio. Okay, so we know from some of the correlations that are observed between central black holes in galaxies and the luminosity of the bulges in which they sit, as well as the velocity dispersion of the bulges. We know that these correlations are seen. These are empirically derived correlations. And these are very suggestive that the galaxy somehow knows about the central black hole, central supermassive black hole, right? And so what we want to do is to try and understand, as I said, how to couple something that's at a very small scale to the scale of the bulge, right? And it might be a little puzzling, and one of the reasons it's puzzling is because if you remember, we talked about, I keep stressing the size scales because that is kind of key in the kind of modeling that we're doing, coupling scales, right? So for a black hole, we can define another sort of scale outside the Schwarzschild radius, obviously, much outside, which is the region of influence, which is GmbH over sigma squared, which is the velocity dispersion of the inner regions, the bulge of a galaxy, if you will. And you actually see that it's 3 parsec for a 10 to the 7th solar mass black hole. That is really, really tiny, right? So that's the region over which the gravitational potential of the black hole dominates the dynamics of the system. Beyond that, the galaxy takes over, right? So 2 puzzling things. First is that this time scale, this length scale seems really, really tiny. So how can the bulge actually know about the black hole? But the answer already was the energetics. So the kind of energy that the black hole can provide, as long as you can tap that energy, couple it somehow into some kind of outflow, then you can actually have impact of the black hole well beyond the region of influence. Okay, so because that's the puzzle in terms of the observed correlations. The observed correlations all pertain to scales showing you the impact of the black hole on extremely large scales, right? So luckily what it is the amount of energy that the accreting black hole can actually supply to the galactic nucleus. Now, if you look at the energy that is supplied from accretion, you actually find that it's about 2,000 times, a few thousand times the binding energy of the bulge. So when you look at the energetics, there's something more contradictory. You're like, okay, that means you have more than enough energy to completely unbind the bulge, which means whatever coupling you actually come up with for the nucleus with the larger scale has to be very inefficient. because otherwise you'll destroy the bulge. There's enough energy to basically detonate, if you will, and destroy the bulge, right? So whatever coupling, whatever feedback model you develop, ultimately will not be all that efficient, right? Okay, sorry. Yeah, so this is just, I'd forgotten that I actually had the slide. Okay, there you go. So, okay. So, but on the one hand, it's not surprising that you see these correlations because ultimately, right, it's the same gas reservoir that's feeding your black hole from which stars are forming and so on and so forth. So anyway, so the goal has been to try and understand where, how to establish this coupling of scales. Now, the other interesting thing that is observationally seen, right, and ultimately, I guess the reason why I'm speaking at a place, that at a summer school on black holes and galaxy formation, is that when you look at the globally average star formation rate as a function of cosmic time, and in green, you are seeing the black hole accretion, the mass density of accretion from black holes, and that has been multiplied by a factor of about 3,000. It's much lower than the energy output from stars that you get. So it's but to just show you, you see that they track each other rather well. So what that's telling you about any feedback prescription that you develop is that star formation has to be part of this feedback prescription. So, there's going to be feedback between the accretion rate onto the black hole and the star formation rate, right? And so any model that you develop is going to have to naturally kind of account for that. So first, let's look at this m-sigma relation, which is the correlation between black hole mass and the velocity dispersion of the bulge. So there's a very, very simple way to understand how you could have that relation. And you can look at the extreme case. Now, look at the accretion luminosity that is produced by the black hole. And you can say, what is the limit? The limit is when the back reaction of the radiation with the accretion flow is such that you unbind the disk. Basically, the radiation output exceeds the binding energy of the inner accretion disk. Then you destroy the accretion disk, right? So that's kind of a drastic limit. So if you make those arguments, you naturally get a correlation, a relationship between black hole mass and velocity dispersion, whatever central velocity of the halo, to the 5th power, okay? And then if you develop a feedback model in which you have some momentum-driven winds that somehow limit the stellar luminosity, because remember, ultimately our goal is to couple the black hole accretion rate to the star formation rate, then there have been sort of two kinds of models, one proposed by Murray, Quartert, and Thompson in 2004, and a bunch of models that we've been working on in various guises for a very long time. And so in these models, when you momentum-driven outflows really regulate and connect the large scale to the small scale and dissipate, move mass and energy around on these scales that will affect both black hole accretion and eventually the star formation rate as well, you find that the mass of the black hole will be proportional to sigma to the 4th. So without doing anything fancy, you can already see that from theory, from just an understanding of how to couple the small scale to the large scale, we can predict that the slope of the m-sigma relation should be somewhere between 4 and 5. Okay, so we can now sort of explain what that slope with just these sort of simple arguments. But obviously, we need something much, much more sophisticated. And so what we're going to do, there are a bunch of different models. They all have pretty much the same elements. There are some details that are different. So I'm going to focus, as I mentioned yesterday, the model that Andrew King has developed and that I have worked on. And as I was mentioning, we are writing this review, and what I'm showing you today is what should have been a written-up review about a year ago, but it's not. But anyway, so I'll be focusing on this particulars. I'll be showing you the particulars of this model. So basically, this is also a point that I already made. Somehow I kind of blanked out that I had. Okay, so let's look at what are the ingredients that we have in our model at the moment, right? That we can actually calculate. So we have the momentum outflow rate for a source. So we're looking at a case where you're accreting at the Eddington limit, and we can see what kind of typical velocities for the outflow that you can get out of if you directly couple to a wind, to an outflow. And so there you see that, just simple energetics tells you that you could already get easily outflows with velocities of about 0.1 c, which is kind of nice because, as I told you, way outside the inner regions, that's what you are measuring for sources. So you can then calculate what the energy outflow rate is, and you find that the energy outflow rate is actually about 5% of Eddington. And now this also squares very nicely because remember when we did the simple argument, we said that however you couple, it has to be kind of inefficient, right? So this tells you that you can accomplish that with an outflow. So how do you do that in detail? So I will sketch out this model. And the details of this model, one kind of nice version is presented in King and Pounds 2015. It's one of the references at the start. So this outflow model, to couple the small scales to the large scale, has two regimes, two ingredients, basically. So essentially, the black hole will power an outflow, and this outflow will collide with the bulge gas, and it will shock. The question is, there are going to be two stages depending on what happens after this shock. So, and the two regimes are, the two sort of possibilities are, you first start out, and we'll see what are the physical conditions that will make you go towards A, and when do you go towards B. So it'll turn out that we can transit from A to B quite naturally, okay? So in the first case, you have a model in which the outflow gas can actually cool, and that's a momentum-driven flow, and so thermal pressure is negligible for this scenario. And then there is a stage in which the shocked gas can no longer cool, and that's an energy-driven outflow. And here, the pressures start to matter, and the thermal pressure actually is in excess of the ram pressure. And you will say, okay, but who's doing the cooling? What's the cooling? Well, we have, a pretty nice, strong radiation field in the center from the quasar, which we tap, and the cooling is actually Compton cooling. And so what we really need there is, therefore, the right reservoir of electrons, which we do because we have the torus. We saw the structure, right? So we have a lot of matter that we have along the line, along the accretion disk to accomplish these two scenarios. And so let's now spend a little bit of time. So first I'll show you schematically. So these are the two sorts of regimes in the feedback models so these are the feedback models that I will show you that we have implemented into semi-analytic models and the consequences of them. So they broadly fall into these two regimes. So it turns out that when the mass of the central black hole is, so this is, remember, this is during the process of black hole growth, right? And so this is prior to the m-sigma relationship being established. So you're coming towards that relationship. So when your black hole mass is not large enough, then you are in this cooling regime. And once your black hole has landed on the value of m-sigma, so it has reached the value appropriate for the galactic nucleus it is sitting in, the bulge that it's sitting in. Remember, both of these things are dynamically moving all the time, right? You're making stars, you're changing the stellar mass, and you're also assembling the black hole. But if you take a snapshot and you can see what are the two stages, these two stages are when the black hole has not yet assembled to be on m-sigma, so it's not massive enough for the bulge that it's sitting in. And in this case, it is at the mass or has exceeded the mass of the bulge it's sitting in. And that's when you kick into, there's no cooling, this is an energy-driven phase. And this is a very dramatic phase, because in this phase, you can actually blow out a huge amount of gas. You can actually do an unbinding. And what's very interesting about this stage is at the end, you actually can come up with a limiting mass for the black hole. So we can actually come up with an understanding of what is the final mass of the black hole that will basically choke its own accretion flow. Right? So it flows very nicely, because this the kind of limit that you get here is nicely explains the masses of the most massive black holes, the ultramassive black holes that are being uncovered in the local universe by, in the centers of BCGs, for example, right? And the massive survey that Changpei Ma and her collaborators are doing are sort of uncovering those black holes. And so we have in this scenario a nice way to kind of explain why and how those masses are what they are, given the bulges that they live in, right? Okay, so I'll try to outline this model and show you what the sort of the physical setup is. So the physical setup is you have the accreting black hole, and you're driving, so you are converting the accretion luminosity into a wind. So this is a mechanical wind. Remember, the radiation itself, we see these luminous quasars. So the radiation on its own can't do a whole lot. It's just escaping and it's arriving at us. So we need to tap a portion of it, convert it into some kind of mechanical luminosity that will drive a wind, right? So that's what is driving this wind. So you have a wind, as we saw, you could drive winds from just the back of the envelope argument, something like 0.1 C. So then we expect the wind to have a shock. So, and you are sweeping up gas that is in the ISM, and you have, it's sort of mildly shocked gas in the blue region, right? And then you have an outer shock that is being driven out into larger scales. Remember, this whole goal is to kind of push things out to much larger scales, right? Well beyond the radius of influence of the black hole, and into the bulge. So you're driving this outer shock into sort of this ambient gas, and this ambient gas is the sort of the ISM that Eve has been talking about. So I'm, of course, going to be very hand-wavy about all the properties and so on, but by and large, this is sort of the scheme that we're going to, yeah?
Why you're saying that the blue is mildly shocked at 0.1 C, I would expect that to be, many hundreds of millions of Kelvin extremely shocked.
Well, I mean, I think it's mildly shocked relative to the next scenario that I'm going to talk about. Sorry, it's not. Yeah, mentally I'm comparing the two cases. Yes. Yeah. Yeah. So let me just go back again to kind of show you. So this is the scenario that we are looking at. So you have the momentum and pressure are conserved for this shock. You go here, and you very, very rapidly cool. And this is sort of the structure that we worked out in terms of just the energetics that will allow you to basically couple energy onto this scale from very, very small scales, right? And let's see. So and the contact discontinuity is sort of here. And yeah, it's a pretty, the jump conditions are, it's a pretty strong jump condition. So if you look at and I guess this answers your question in terms of temperatures. Yeah, so you can have really high energies imparted to the material in the wind shock, and it's extremely hot. It's hotter than the radiation field of the quasar, which, remember, we calculated yesterday, was about 10 to the 7 Kelvin. And so then you can calculate what the Compton cooling time for this plasma is, and you can put in the input radiation as that of the intensity of the quasar, say, accreting at the Eddington limit. And then you can see that this the Compton cooling time is actually shorter than the shock travel time. And what that tells you is basically it gives you a critical scale. You can calculate by just equating them. You can see by saying that you can calculate what a critical scale is where they would roughly match. And what you find is then you are able to couple for a 10 to the 8 solar mass quasar, you can get out to 20 parsecs. So now you have a description of a wind, of a cooling wind that is momentum driven, that can actually couple the inner regions to about 20 parsecs. Okay? And so basically you have very strong cooling, and so the shocked region is actually very narrow. It's nearly isothermal. And so this is that picture that we're talking about. Okay? So now let's look a little bit more at how much of the bulge we are actually able to impact, right? So if you have a typical bulge, let's, for simplicity, model that as an isothermal sphere. So then the density is just sigma square over, so it's a 1 over r square with a sigma square. And because it's an isothermal sphere, the sigma is obviously constant. And you can calculate the mass inside any given radius. And most of this mass, as you know, is going to be in stars. And let's just say that you have a gas fraction. A fraction of that mass is actually in gas. And to compute that, we just use the cosmic overall gas fraction of about 10% or so. So then we can actually compute what the gas profile, when we assume that the gas profile is the same, but we can compute the gas mass, right, in that region as a function of r. So now what we want to see, now remember that matter that is actually swept up is going to be gas that is in the bulge, which is distributed like the isothermal sphere. So we have the total mass is basically the sum of dark matter stars and gas that's in there, and the swept up gas mass, as we just saw, has this gas fraction. Okay? So now what you can actually calculate, the impact, you can calculate the motion of this shell with the swept up gas and see how that evolves in time and how that evolves as a function of radius, right? So we can write out the equation of motion for the shell, and this m sigma here, that m is now the black hole mass, guys, right? So that m is the black hole mass. M total is the total mass, but m without BH is actually the black hole mass. And so what you find is you can do some simple, you can look at this equation, and you find that if m is less than m sigma, there is really no solution at large radius. So this outflow can take you out up to a point, after which you need a different mechanism to push further out, right? So you can see where this is going, right? So that's just basically telling you that you start out with a momentum-driven flow, after which you basically have to move to an energy-driven flow, okay, and larger scales. And that's because, why is there no solution? Basically, if you think of the power that you have when you've tapped the Eddington luminosity, there's just not enough thrust to lift up and move the shell any further. So basically, you tank out, you tap out after a certain critical radius. Okay? So you can reach only so far. But notice, if m is greater than m sigma, then you find that the shell can be expelled completely. It will escape the nucleus. It will escape the potential. Okay? So you find these two cases of solutions, and that kind of nicely maps onto the two regimes that we were talking about to couple the small scale to the large scale. So of course, there's a critical value. There's a critical value at which this transition happens. And that critical value is roughly 10 to the 8 for the bulge mass. So remember, this is a critical value now for the bulge mass. So once your bulge has also built up to a certain critical value, right, then you have this transition. You actually have this as the mass when the black hole mass. So there's a limit on the black hole mass that we've said once the black hole mass approaches the bulge mass, right? This critical value determines the switch in feedback mode. So, and this, of course, is, it's not surprising that this is close to the m sigma value because we've used the very same kind of arguments to derive what the m sigma relation should be when I talked about unbinding the disk and so on. It's pretty much the same argument. It has to do with the Eddington trust. So the supermassive black hole, well, basically the hole will grow till you are unable to expel the gas that is feeding it, right? So I remember I did a simple hand-wavy argument and I got that, and here I'm just telling you that there's a shell structure, there's cooling. I mean, they put a little more physics into it, right? So basically, till you reach this sort of critical mass, you actually grow the black hole, and in fact, once you exceed that mass, when the black hole mass exceeds this critical value for the bulge mass, you don't grow the hole anymore. Okay, you sort of stop black hole growth as well. This is kind of nice in a way because you can see that there's observations on galactic scales that have to do with red and dead galaxies where the AGN has also shut off, and you've also shut off star formation. So it looks like this is an interesting limit that you can then couple to that. So basically, you have these shells before in the momentum-driven regime. These shells are still confined around the black hole. You can't completely expel them. But then after you have exceeded, MBH exceeds that critical bulge value, you can actually expel those shells, and you can expel matter. So essentially, once you have reached, the black hole has reached the critical value for the bulge mass, you can actually transit to, you actually need to transit, you will and you need to transit to an energy-driven outflow. Okay? So what happens again is when the mass of the black hole exceeds that of the bulge, this radius on which you can couple the energy grows. And so you can go well past your RC, so you can go well past your 20 parsecs. So. And in this case, what you have in an energy-driven flow, so here what we need to calculate is the PDV work that is done by the gas on the surroundings, right? So, and now the equation of motion will contain the sort of post-shock pressure that you have. So the end point of our previous outflow solution are going to be the initial conditions going forward for channel B in the outflow model. So the wind shock, basically what you have is you'll have the shock that is sort of locking around the cooling radius, which was that critical radius RC. And because now the sound speed is going to be really high, you have an extended region that has constant pressure because, and all the way out to a very large radius where there's, this swept up gas can actually go out to a much, much larger radius. So now we're looking at this scenario. So you have a very fast wind again, and now you have an adiabatically expanding wind, and you have that pushing out to much larger scales. And here, the conserved quantity here is energy. And so then you can calculate for this instant. So the thing that's going to be different is that you're going to have some PDV work, so work done per unit time that shows up because the pressure is important here, and the pressure here is the gas pressure and the ram pressure of this shell, of this moving shell. So when you put that in, what you find, you can write out the equation of motion for this shell, and you find a bunch of, so you don't see any easy analytic solutions, you've got to numerically do it, and you see some interesting features of the solution. And here is the velocity of the shell as a function of time, and the velocity of the shell as a function of radius. And you find velocities of the order, rising to the order of about 2,500 kilometers per second or so. And what is interesting is that your velocities drop off after, because then you no longer have the kind of density outside the bulge to support this, so you fall off. What's interesting is the time scale on which you actually fall. That's about 10 to the 6th years. So the quasar has now shut off. Remember, there was sort of a rough duty cycle that we saw for quasars of the order of the saltpeter time. So basically, once the quasar shuts off, your wind basically oozes out. Okay? And so it sort of persists a little bit, but again, kind of starts to ooze out even after the quasar gets shut off. Okay? And so when you have, as a function of radius, what you see is that you are able to now, so what is nice about this is that, as you can see, we are very excited because you can now move to KPC scale. We've managed to push out from like parsec scale to couple to KPC scale. And so what the observational manifestation or test of this picture is going to be that we will argue that you can actually, in this kind of model, explain the high velocity outflows at fairly large radius. So if you remember Mike Iraculis's diagram that I showed you, this is observationally tractable, this region, right? So the question now is to see if we can match those models. Okay? And in a paper in 2012, and remember this, I modeled it as an isothermal sphere. You can do much more interesting things. We can, you can build the bulge as a Hernquist model, and it all works. So it's pretty robust. You get the same qualitative behavior. And you can then calculate, for example, in detail, how the velocity of the outflow as a function of the equation of state of the gas, right? And you can then calculate the mass in that outflow, the mass outflow rate. So you can very simply, numerically, of course, calculate all of these quantities that are going to be relevant for matching with observations. Okay, so once you perform, so this is the sequence. The sequence is you start out with an accreting black hole, say it's accreting at the Eddington rate. You have a momentum-driven outflow that is powered till the black hole mass is building up. Once the black hole mass and the bulge becomes equal, so it will land, it has the mass to land on the m-sigma relation, then you switch from the momentum-driven outflow to an energy-driven outflow, and you are able to then couple from parsec scale to KPC scale. But the consequence is that in the energy-driven outflow, you are actually pushing the shell out completely. You're getting rid of the shell, shutting off the black hole, and you're getting rid of huge amount of matter in the outflow. And so at this point, the galaxy will become red and dead, which is great. So this is one of the, observationally, this is a sort of sequence that is seen. And so we want to have scaling relations that, for feedback from the black hole, that can eventually kind of explain this phenomenon. So you'll see when I talk tomorrow and show you the implementation in models for a population of black holes, the modeling the growth and evolution over cosmic time, I will be using all the scaling relations that I've shown you and the motivation for them that I've shown you from basic accretion physics, right, from simple models. And you'll see one of the key scaling relations that we will be taking from this outflow model is when two galaxies merge, so this will all be done in the context of lambda CDM and mergers. So when two galaxies merge and the two black holes will merge, right? We want to know, as after the merger, how much does the black hole actually grow, right? So is it going to grow because you have a large gas supply that's delivered to the center, when do you cap the mass of the black hole? And so the capping is obviously going to come as soon as you reach the black hole mass being equal to the bulge mass for it to sit on the M sigma. Okay, so because that's the critical value here, right? And after that, the quasar basically shuts off, but the cap, the mass cap on how much a black hole can actually grow in a simple sort of semi-analytic model is set by this outflow model. Okay? So that's where this outflow model comes in handy when we are going to look at the ensemble properties tomorrow. And of course, there are some really interesting things that you can work out further during the energy-driven outflow stage. You have this shock, and it could be Rayleigh-Taylor unstable, and then you should be able to see some further features of these instabilities. You have like a two-phase medium, and there's a lot of work that's been done on how gamma rays impact sort of molecular and molecular emission are produced. So you can actually describe lines that you would see observationally, even within this sort of simple model. So let me just quickly show you how, what we argue are observational features that are explained by this simple model. So this is data of M82, where you see the O3 emission. And what you are seeing here is, this is about 400 kpc. So the kind of models that we have been able to push out, right, they go out to a few kpc. So, so these are the kinds of, the attempt is to use our energy-driven outflow models to try and explain. And Contursi and collaborators have tried to do that. And so then we have some of these Markarian objects where we actually also see and measure outflows. And here, the velocity of the outflow is inferred to be 1,000-ish kilometers per second. And this is the kind of number that we can plausibly explain with this model. And so we can kind of output. So this is work that Contursi and others have done, and collaborators. So you can actually, from the observation, extract the parameters and see, in the context of this model, how they fit. So it turns out that we can sort of infer from the observations, we can kind of match with the mechanical luminosity, the mechanical energy, are roughly what we have predicted in this model. So there's a lot of interesting data, and the model is still heuristic, but it can be developed much, much further and tested. So, I mean, this was one recent, as you can imagine, in terms of further observable tests, these models actually predict a relationship between the kinetic power of the outflow and the bolometric luminosity of the AGN. And so this is, and what this allows us to do is kind of then figure out from the data what that efficiency should be. And remember, we got roughly 5%. So that looks reasonable compared to what we've done. So this is a nice, this is just a nice slide for you guys to have, because it just outlines the work that was done by Tom Basie and collaborators, which is where this plot is from. And basically, the bottom line is that the energetics of these winds that are detected is consistent with sort of the energy conserving mechanism at the later stages. Okay, so I think I might actually be done. Let me see where I was planning to go next. I've kind of forgotten what the next slide is. So obviously, the detailed work that remains to be done is to couple the physics of star formation explicitly, right, with the kinds of processes that Eve has been talking about, detailed processes in the ISM. In this model, it's difficult, but what we do have is we have physical quantities that are available to us to start with a setting up of the initial conditions for the ISM. that has had an outflow driven through it by a black hole. And so we ultimately need some kind of star formation model that could then help us. So, observationally, we know that this is sort of the sequence that we have, right? So you initially have star formation in terms of how to link up to the star formation history of the assembling stellar mass, right? So we're trying to match up the assembling black hole mass to that of the assembling stellar mass. So you expect star formation at all radii, but then you have sort of some kind of bulge formation, be it through mergers or whatever. And then you have, we see, this is observed, right? So this is the sequence that's kind of inferred. That you see a quenching of star formation in the center, and the outskirts could still form stars, and then the quenching sort of spreads out. And so the idea is that this model that I talked to you about needs to be refined in order to kind of explain in tandem with the star formation rate, history, evolution, in sort of a template nucleus. For the moment, as I said, all I'm going to be using from the picture that we've developed so far is when talking about an ensemble of black holes, a population of black holes that are growing, I'm going to be taking the cap mass. How do you limit the mass of the black hole once you merge in these semi-analytic models? After merger, post-merger growth, what is the final black hole mass? But in the models that I'm going to show you, Rachel has much more sophisticated models in which this coupling is already done. Okay, so she has a semi-analytic model in which the star formation properties are linked with the black hole growth already. In the model, the demographic models that I am going to show you, I don't explicitly model the star formation. I just assume correlations between halo mass and stellar mass, relations, and so on. So and the reason for that is what I am interested in is the demographics of the black hole population. There's a lot to be explained there. And then there's obviously what kind of hosts are they sitting is the bigger question, right? So, but because most of my science has been sort of motivated really by for understanding black hole growth, mergers of black holes, LISA events, et cetera, I'll be focusing only on the assembly history of the black hole itself. But I just wanted to tell you that there are other models like Rachel's, and then Richard Bauer and collaborators have models in Durham where they've already coupled in the semi-analytic framework, not simulation, semi-analytic framework. Again, they've coupled the star formation, and the way star formation is incorporated in those models is motivated by simulations, right, as well as observations. So let's see, what else did I have to say? Oh, yes. So remember, another feature that we would like to have is some kind of explanation for the observed variability in AGN light curves, right? And so the outflows may actually be kind of episodic. That's one way to explain time variation. And therefore, the AGN driving could be variable. So this could tell you something about the time scales. Like 10 to the 5 years is a reasonable time scale, is the appropriate time scale for changes on the geometry of the inner regions, right? So what you find is that you can compute in the models that I've shown you what is the typical kind of variability time scale for characteristic variation. And the sort of flickering time scale that you get is kind of nicely 10 to the 5 years, which sort of matches the observations. So this is further, the duty cycle is about 10 to the 7 years-ish, 10 to the 6 to 10 to the 8 years-ish. And so the progress of the outflow that the simple solutions that I showed you, it may be actually intermittent, because if there's variability in the source on small scales, that's going to be reflected downstream in terms of the variability in the outflow velocity downstream. Okay, so this is another element that we're going to include, which is the variability. And so just to show you that there's been some sort of very interesting new data where you have massive black hole, and in this case, you are seeing what could be shells from various outflows that have broken out and gone out in the energy-driven phase. So one other thing, one final thing that we can do is at the moment in these outflow models, I actually did not explicitly assume anything about the relative ratio of the black hole mass to the mass of stars in the bulge. So, but what I can post facto use what I have derived in terms of the outflow properties to actually compute what that is. And interestingly, one finds that you get a black hole mass over bulge mass that is about 10 to the minus 3. And this epsilon star is sort of, globally average, some efficiency of conversion into stars. Okay. That is, which is in the makeup of the bulge. Okay. So I think what is interesting about this picture that I've developed so far is that the establishment of the M sigma relationship, right? The fact that the supermassive black hole mass is proportional to sigma to the fourth is set on very, very small time scales. And the assembly, so the assembly of the black hole and the assembly of the bulge, that this relation, the black hole mass bulge mass relation, it follows from the treatment that I have shown you, is they are actually acausal, right? So the bulge is assembling, the black hole is assembling, and they just interact through these outflows, right? And that they do not actually influence. So that's one of the sort of predictions of this model, which means that depending on the details of the outflow, we will derive a slightly different tilt for the M sigma relation that is measured for, say, cluster galaxies and galaxies in, because you are living in a different environment, how far out the outflow can go is different. So the gas distribution is would be different, right? Yeah, I think that's maybe too strong, that they don't influence each other. Like, you can't talk of any one of them as causative, is what I mean. You can't say that it's the black hole that determines the bulge mass, or that the bulge mass determines the black hole mass. I think you'd agree with that. It's not particularly controversial. Yeah. Yeah. Yeah, yeah. Sorry, I think that was the wrong, not influence. I mean, they don't actually. Okay. So, the one other thing is that there are lots of cute little, because we have a nice little analytic framework. You can do a lot of simple things and see what you can measure. Can you actually correlate to something that's observed? So we can actually work out what is the optical depth of the ISM into which the outflow is expanding, because basically we know that the amount of luminosity that we're sort of tapping is about 5%, right? So we can just put that in, and we can calculate the optical depth, tau, in the bulge. And basically, what you can see is that the optical depth goes as sigma squared over r. It's just a cute thing. It's not particularly consequential. What else can you see? So basically, you get that this, you can see from the way this falls with r that it gets very large for small r. It's 1 over r dependence, right? And so basically, the luminosity gets trapped at very small radius. And so the radiation will tend to push the ISM into a shell of mass, which we can calculate what it is, the mass of the shell. That's proportional to r, and we know that a lot of the radiation gets trapped in the inner regions. So that then tells you that if you trap radiation, that means you're actually moving away from the thin disk geometry. So this is telling you a little bit about the validity of the kind of our models. It's kind of slightly tweaked, basically, right? Because this is not compatible, that the optical depth, as you, oops. Yeah, so the optical depth going as 1 over r basically tells you that, as you're getting closer and closer to nucleus, the optical depth is really large, so you trap a lot of radiation, and then you are going to have a puffy disk. You're not going to have a thin disk. So this is a caveat. Okay, but we can talk about the trapped radiation will see an effective optical depth, that is the optical depth plus the optical depth of the shell itself. So you can kind of compute what it is, and you can see that this becomes optically thin for a particular value of r, and we call that the transparency radius, just to estimate what that is. And you basically find that the transparency radius is of the order of 10 to the 7 Schwarzschild radius. So basically, at this point, the shell, right, this is the ultimate fate of the shell. So basically, your shell is moving out, and then all the radiation basically escapes, because now you're transparent in the optically thin regime. And you're sort of end of the shrouded phase. So remember, one other thing we would really like to do is to explain the obscuration in galactic nuclei, right? So this torus and the production and the obscuration that the torus produces. In the context of this feedback model. And so UFOs are ultra-fast outflows. And so this is the data that shows you basically roughly at about 10 to the 7, 10 to the 8, you see a lot of radiation can actually escape. And this is measured in sort of the warm absorbers that are seen in the X-ray, right? So, then one can look a little bit into what determines the transparency radius in terms of the actual physical process, like how does the opacity change? How do you become optically thin? So there's some interesting kind of correspondences we can make with observations at this model that I think make this sort of feedback model viable. So some of the other interesting things which are not incorporated in the model that these outflows can do for you, which are consequential for the observations, is that we see supersolar abundances in AGN spectra. So basically and I said this is episodic, so you need a lot of mixing. So these outflows and the gas in these outflows will facilitate a lot of mixing, because you will be repeatedly sweeping out gas and stars and stuff, gas and stars that are roughly the same age and enriched, and then when you settle back in, you have mixed the metals, and that can explain how you can get some very gas-rich material around the centers of AGN. And people have tried to use this mechanism of driving out flows to rearrange the detailed dark matter distribution to soften the spike in the centers of dark matter halos that CDM predicts. And it kind of explains why you see, and I've very vaguely, purposely written little, because, there is some. So that star formation appears to be somewhat slightly suppressed in AGN hosts. And yeah, so I think we have a mechanism for sort of spreading metals, which is sort of these energy-driven outflows. So I just want to stop here. This is my final slide. And so there's a slightly different model. And this model is one, the details are different, but by and large, it's the same, except that this is sort of in the context of chaotic accretion of clumps, right? Clump chaotic accretion is what CCA is here. So this is a model that's developed it's a paper I like very much. by Gaspari and Sadovsky. This is actually a numerical model. This is a GRR MHD code in which they've implemented and studied the coupling, once again, of these very small scales to very large scales. Basically, they find also that they can explain, this is a model that's very akin to what I've been trying to do, but much more sophisticated, much more sophisticated and implemented in simulations. So let's see, what else do I want to say? So I think I'll just stop here and say that, I think at this point, I have developed all and given you really good motivation from basic accretion physics for many of the scaling laws that I am going to extract from what I've shown you so far into a framework where I track the growth of a population of black holes embedded in cold dark matter halos over cosmic time. Yeah? So, and so that's what I'll finish with next time. And I'm hoping to show you how, with just these elements, you can actually explain the observed luminosity function of quasars as a function of redshift. You can actually observe the integrated emission from the X-ray part of the emergent spectrum of these accreting black holes, the X-ray background, and the cosmic infrared background. We can also explain the mass function of black holes that has been measured locally, and that is derived from, say, reverberation mapping and so on and so forth. So, so you can build a very powerful set of models. And what is advantageous about that kind of modeling, the simple modeling where you have well-motivated scaling laws from the physics, is that you can change. You can change parameters, you can change the efficiency, and you can see the downstream effect. You can see which parameters tune the low luminosity end of luminosity functions. What is the information? Because the low luminosity end of quasar luminosity functions, both in the optical and the X-ray, these very faint sources are yet to be detected. They're below the current level of our instruments. But they actually carry a rich amount of information, which is why we are constantly going for larger aperture telescopes and higher resolution telescopes in space and here, because we want to uncover the faint end population, because that's also the ubiquitous end of the population, right? The brightest sources are actually rarer, and we've kind of found them. They stick out, right? So it's the low luminosity end, and so hopefully when I speak on Friday, I can sort of show you very clearly which scaling law and which assumption actually changes the slope and the amplitude of the low luminosity end of the quasar luminosity function, for example. And it turns out that the impact is different on high redshift and low redshift. And anyway, so we'll see the consequences. And so the advantages of these kinds of models is that I can actually implement two different kinds of accretion, as I showed you, right? I can do the radiatively efficient one, which is the Eddington one. Then I can implement a radiatively inefficient scheme, which is the one in which the accreted luminosity is proportional to the log of the accretion rate. And I can play and see, what features of luminosity functions I'm able to or unable to reproduce with each of those. So I'm hoping to give you all a really good flavor of how you can go from simple, and I don't want to, and one of the reasons I'm sort of selling these models is, a lot of the subgrid models that people implement in simulations are these, right? So I mean, this is the motivation for many of the subgrid models as well. It's just that we are going to adopt a much simpler scenario in these semi-analytic models. So anyway, I better stop here. I think that's it, yeah. And I think, this is the takeaway for the outflows.
So I thought we were going to have a lot of time for questions, but it turned out the last slide actually had a fair number after it.
Yeah, sorry.
But so it is lunchtime, but if there's any quick questions, we can of course.
Well, I'm also hanging around, so
Yeah.
either way is fine. Yeah, hi Betsy, yes. Okay. Oh, there's a thing here too? Wow, okay.
Okay, I think. So you showed that the energy-driven
Just
model,
to-
sorry, the energy-driven model can explain the outflows from like M82, which are very broad. Can they also explain, let's say, the outflows of Cygnus A, which are like those, like the radial lobes, which are very tight in the beginning and then blew up?
Breakout. Yeah, no, we haven't done I think broadly speaking, we can kind of explain the energetics, but haven't done the numbers to tell you if we can actually match the spatial scales and what kind of, whether you still get 5%, et cetera. I don't know yet, yeah.
I was wondering, when you, in the derivation of the M sigma relation you showed, you assume a density profile for the bulge gas, and I was wondering whether it changes the normalization or...
It changes the normalization a little bit if you choose a different profile.
Not the exponent?
Not hugely, no. Because, ultimately it's the total mass enclosed, that's not too different.
So I think I've seen a small population of spiral galaxies observed that have black holes but no visible bulge, and I was wondering whether those kind of came out of the model or not.
Yeah. I'm going to leave that to Rachel to sort out the galaxy part of how, in the cases, you're saying how do I even apply this model if I don't really have an assembled bulge, right? Because I'm then tagging it, the model is somewhat limited in that sense, yes. I can't explain. The nice thing about having the bulge is, you have a scale and you have a reservoir of gas that's in there. It starts in gas, but I actually assume that there's some Fg times the mass in gas. Yeah.
But they don't come out as just like a very young, early stage of formation before the bulge.
Yeah, I think that the argument there would be that these are cases where you probably have like the momentum-driven inflow, when basically you haven't assembled stellar mass in the central region that's comparable to the black hole mass. But those bulgeless galaxies are, we've got to think more about how to come up with a sequence for them, what's going on. Yeah.
Can you comment on some of the claims that you can get these black hole galaxy scaling relations just from hierarchical assembly and the central limit theorem?
Yeah.
And can you distinguish between this?
Yeah, so that's a great point. So, I think there was a paper by Chen, I think in 2010, that actually showed that within the sort of the standard merging hierarchy in a sort of a merger-driven scenario, you can actually just get a relationship that looks like M sigma from just lambda CDM without doing anything else, just the statistics of mergers. So remember, in what I showed you, I didn't actually, I started out by saying that you could have you can have any number of arguments that give you sort of an M sigma type relation. So I did not list the central limit theorem argument there, but I gave you two, one in which was just the unbinding of the disk argument, and the other one was the star formation, luminosity of star formation, Elliott's argument, right? So one gives you sigma to the fourth, the other gives you sigma to the fifth. And yes, another way to account for that relation, because these outflow models are not giving you an explanation for that, right? They just follow from sigma being MBH being either sigma to the fourth or sigma to the 5. So what I've shown you in these models, that we've actually assumed sigma to the fourth. So, and the data, one can argue, I think there was a recent paper that showed that if you fit the data now with the increasing number of black hole mass estimates that are growing, that maybe the slope is really closer to 5 rather than 4. So I have not looked very carefully at that. There's one more question, maybe. Take that.
Hi. So I was just wondering if you could comment on, so there are galaxies that, or I think it's understood that below a certain massive galaxy, there are no supermassive black holes. but there are nuclear star clusters. And so I was just wondering, like, do you think that these nuclear star clusters have to sort of become like black hole seeds?
Yeah, they could, and so watch that space. I'm going to be talking about the various channels for the formation of seed black holes, and nuclear star clusters are a viable scenario to form. But the question, as always with scenarios, is when do they need to kick in? Because of the time that it's going to take in terms of dynamics of the nuclear cluster for the remnant black holes to all merge and give you a seed. When does that effectively start to operate in the early universe? So it turns out that it may not operate early enough to be effective to explain the masses of the brightest quasars detected at 7, but we have other ways to do those guys. So, so I'll talk much more about that in detail on,
Okay, so then we can head to lunch now, and let's
Great.
thank Priya again.
I'm sorry I went a little over.